this video, we're going to look at the idea of continuity, or is a function continuous or not. And so when you're looking at continuity, you want to look for certain things in the graph. You want to look for holes, you want to look for jumps, you want to look at limits, and then you want to look at function values. For example 1, you can clearly see that there's a hole right here in the graph at the point 4, 8. So the first part of this says, what is the limit as x approaches 4 of this function? So to find the limit, you want to look at what the graph is approaching from either side of x equals 4. And you can see that that limit is clearly 8. The graph is approaching 8 on both sides. The function value, however, is going to be the closed point. So to get the function value, you're going to look at this closed point right here at 4, 2. So the function value is 2. And so the idea is, if the limit and the function value do not match, that means the function is not continuous. The non-mathematical definition of continuous is that you can trace the curve without picking up your pencil. And you can see that you cannot do that with this curve, because when you get to the hole, you have to pick up your pencil and move to the other side of the hole. In example 2 here, the limit as x approaches 4, if we look on the graph is just, both sides of the graph is approaching the point 4, 8, so the limit is 8. The function value is also 8 at 4 because it's a nice smooth curve, and so we can say the function is continuous at x equals 4 in this situation. In the next example, again, we have a hole. Again, the limit here would be 8 because both sides of the equation are approaching 8, or the graph. The function value, however, at 4 is undefined. There is no function value at 4. Because of the hole, there is no closed point at 4. So again, the limit does not equal the function value, which means this function is not continuous at x equals 4. Again, you cannot trace this graph without picking up your pencil. In this last example, you can see that we have a jump. And so if you look from the right side of the limit, it's approaching 12, but the left side of the limit is approaching 8. And if you remember from limits, a limit only exists at a number if the left and right sides approach the same number. So we have to say that this limit does not exist. The function value does exist. There is a closed point at 4, and it's right here at 4, 12. So the function value is 12. However, again, the limit and the function value are not equal to each other, so we would say g is not continuous at x equals 4. And again, so we cannot trace this graph because of the jump without picking up our pencil. So the definition of continuity, or a function is continuous if, first of all, the limit as x approaches the number, some number, any number on the domain, of f of x exists. So the limit has to exist. The function value at a has to exist. And most importantly, the limit as x approaches a has to equal the function value at a. So a graph is only continuous if the limit equals the function value for all points. So if we look at this example, this one has an infinite asymptote in it, vertical asymptote, right here at x equals 0. It says, is 1 over x continuous? Now, most places on the graph, you can trace this without picking up your pencil. There's only one place where you do have to pick up your pencil, and that's right here at x equals 0. So you would say, this graph is continuous everywhere, or continuous for all real numbers, except at x equals 0. So basically, a graph is not going to be continuous at a hole, a jump, or an asymptote. And that's what we call our discontinuities. That's where the graph would be discontinuous. Holes, jumps, and asymptotes are where you would have to pick up your pencil. For a whole, a lot of times the limit value does not equal the function value. For a jump, same thing. The limit doesn't exist, so it can't equal the function value. And also an asymptote, the limit doesn't exist and the function value doesn't exist. So those are all places where a graph would be discontinuous. Now, any polynomial is going to be continuous, like x squared or 3x cubed. Anything like that will be continuous. Sometimes they like to give examples with a piecewise function, and they want to say, find the value of k so that the function is continuous. So you've got to check the three conditions of continuity. So you want to start with the limit. So condition 1 is that the limit as x approaches. Now, when you're given a piecewise function, the only place that you might have a problem is where the piecewise function changes its domain. So in this case, it switches equations at x equals 3. So we want to check the limit as x approaches 3 of f of x. We need to know that this limit exists. And the way we're going to do this, because this function has two separate pieces, we're going to check the left-hand limit, and the right-hand limit. So we're going to do 3 from the left and 3 from the right. Now, 3 from the left means less than 3. So when we are less than 3, the function is equal to kx. So I'm going to put a kx here. And when we're greater than 3, the function is equal to negative x squared. So the limit from the right, we're going to use negative x squared. So just like with any other limit, you just plug the 3 in for x, and you get 3k. For this one, if you plug the limit in for 3, you would get negative 9. So the question is, what value of k makes these two limits equal to each other? So we need 3k to equal negative 9, so k must be negative 3. And then we can check that the function value equals the limit. So we check the function value. So if k is negative 3, the function value actually isn't affected by k, because the function value comes from the second piece of the equation, because the equal sign is on the second piece. So the function value equals negative 3 squared, which is negative 9. So if the limit equals negative 9 and the function value equals negative 9, we know that the function is continuous. So f of x is continuous if k is equal to negative 3. So the basic idea is we want to know where the two pieces of the piecewise function are going to be equal to each other. And it's always going to be at this turning point of the domain. So look at example 2. Now we're given another piecewise function, and again, the domain changes at negative 3. And it says, using the definition of continuity, show that g is continuous at x equals negative 3. So we're going to go through the same 3 steps. We need to first prove that the limit as x approaches negative 3 exists, and we're going to have to do that using a left and a right-hand sum. So we need the limit from the left, and we need the limit from the right. Again, when we're doing the left-hand limit, we're going to use the equation that's less than negative 3. So we're going to use the first equation, the square root of 25 minus x squared. And when we're doing the right-hand equation, we're going to use the function that's greater than negative 3, and that's the x plus 7. And then we can just simply plug in the negative 3 for x. So this gives us square root of 25 minus 9. Which is just 16, square root 16, which is 4. And for this one, we're going to plug in the negative 3. Negative 3 plus 7, again, is 4. So the definition of a limit is if the left and right-hand sum are equal to each other, then the overall limit is equal to that number. So we can say since the limit from the left, negative 3 from the left of f of x, actually g of x, is equal to the limit as x approaches negative 3 from the right of g of x, the limit as x approaches negative 3 of g of x is equal to 4. Okay, so that's just condition 1. Condition 2, we have to check the function value. So we need to find g of negative 3. So we have to use the piece of the equation that has the equals to. And you can see that the equals to is here. It's equal to negative 3 at the top. So we're going to use the top equation. So we're going to plug in 25 minus 3 squared, which again we already did when we were doing the left-hand limit, and that is equal to 4. And so the third condition of continuity is to show that the limit as x approaches negative 3 of g of x is equal to the function value. And they are both 4, so they are equal. Therefore, the function g of x is continuous at x equals negative 3.